Hello friends, welcome to lecture 7.7 on applications of continuous wavelet transform. This is the last lecture in the unit on continuous wavelet transform, where we shall discuss applications of CWT in 4 different problems. One is on the detection of time varying oscillations, which is quite important in many domains including process engineering, atmospheric sciences and so on. And the second one is on the detection of singularities, again which has widespread applications. The third one is on the computation of instantaneous frequencies like the way we did with spectrogram. And finally, we shall talk about CWT filtering. Normally filtering is performed using discrete wavelet transform, but it is also possible to filter using continuous wavelet transform, and I will show you how to do that in MATLAB as well. So, let us look at the first application, which is on the detection of time varying oscillations in control loops. As I said, the problem of detecting time varying oscillations is quite prevalent in many domains, not just in process engineering, but also in atmospheric sciences, meteorological data sciences and so on, where one is interested in knowing how the periodicities of certain atmospheric phenomena vary with time. In this example here or in this application I should say, what we are looking at is a large refinery where a number of control loops are in operation, and normally one is interested in the health of these loops pretty much like we are interested in the health of a biological process such as ourselves. And one of the symptoms of poor control loop performance is oscillatory behavior or oscillatory characteristics in the control loops. You do not have to be an expert in control to know that the main purpose of designing a controller and having a control loop is to make sure that variables, process variables or whatever variable that we are controlling is supposed to be maintained more or less very close to the set point without any oscillations. There will be always some fluctuations in the process variable, but those fluctuations should be ideally random in nature. Now, when you have oscillatory process variables despite having control, then obviously there is some serious cause for concern. Pretty much like when the temperature of a human body, which is supposed to be regulated very well by the human body, when it starts oscillating, then there is a cause for concern with respect to the health of the body as well as that particular temperature control loop. So, here we have selected 2 loops from a refinery process. One loop is upstream of the other loop. In other words, both these loops are interconnected, and we do not know which is the cause and which is the effect when it comes to oscillations in these loops. There may be many causes we do not know, but the first thing is to detect oscillations. Of course, detection of oscillations in process variables can be easily done by using spectral analysis like the way you see here. In both these plots, on the top you have as usual the time series data, and on the left panels you have the Fourier spectrum. The presence of a clear peak is an indication, is a very strong indication of the oscillatory nature of these variables. Of course, one can also visually see in one of the series that the variable has an oscillatory nature to it. Now, what is important for us is to know whether this oscillation persisted throughout the observation period, or did it come and go, did it just appear and vanish. And here is where the scaleogram plots, which have now been generated using the wavelet coherence toolbox by Grinstead and Moore. You could generate these plots using the wavelet toolbox as well, but the nice thing about these codes is that you get the cone of influence also drawn for you. So, the scaleogram plots for each of the series reveals the time varying nature of the oscillations. For loop 1, it is clear that these oscillations persist throughout the period of observation, whereas for loop 2 the oscillations really do not persist throughout. In fact, they are intermittent. In fact, if you look at the time durations corresponding to the frequencies where you have oscillations, in fact we have drawn here with the y axis as period, not as frequency, but you can always convert period to frequency easily. So, if you look at this zone which has the oscillatory nature to it, the line corresponding to the period that we have here, we see that in the initial portions for the loop 2 there are no oscillations, and then you see oscillatory behavior which persists for quite some time. So, what does this mean to us? Does it really give us more information than just a Fourier plot? Yes, of course, it tells me that the oscillations here did not persist throughout, and that information is useful to me in root cause diagnosis. So, for example, if only these two loops were there and they were connected, then which one really started off first, or was the controller really trying to fight out the disturbance? If both these had a common source, did the source enter the loop 2 in a delayed fashion, and so on. So, there are a number of questions that can be answered by looking at this scaleogram plot. Of course, you could use a spectrogram also, but we have already studied the advantages of scaleogram over spectrogram. I do not have to really choose any window or window size and so on. All that I need to do is to choose a mother wave, and here we have chosen a Morlet complex Morlet wave for the analysis. One can also look at the phase of these plots to get more information. So, this is to give you a feel of where the scalograms are applied and how they could be applied in detecting time varying oscillations. There are a number of papers that you can read up in the oceanography or the atmospheric data sciences literature where wavelets have been widely applied. So, please go and do a quick search on the literature and you will be able to find many such applications. As far as this application is concerned, here we have managed to figure out that in loop 2 oscillations really do not persist throughout, and that we could use this information in root cause diagnosis. We will not really go further into this because we have a number of other interesting applications coming up. The first or the second in the line is the singularity detection. As I mentioned, this is a very widespread application in many fields, not just in engineering, but everywhere. What is essentially singularity? Essentially, it is a discontinuity, and we already know through our wavelet analysis that a discontinuity at time t naught in a signal spreads itself across all scales in the time scale plane. But importantly, if you look at the scaleogram plots that I have shown here with two different wavelets, the scaleogram, or in fact I do not show the scaleogram here, I apologize, I show here the modulus of the continuous wavelet transform, but you would see similar features in the scaleogram as well. So, the magnitude of the CWT converges to the same point at finer scales. What we mean by finer scales is lower scales. Same point meaning the point at where the discontinuity is observed. So, that is the key feature that is exploited in singularity detection. And this is also the cause for the cone of influence that we talked about, because whenever we perform CWT at the borders we have discontinuities, and the effects of discontinuity at the borders persist for a longer period of time at coarser scales and for much shorter period of times at finer scales. In this problem, we are interested now in knowing what are those features in the modulus plot that converge to finer scales. If I find a feature, or in the sense if I find the modulus of the CWT converging like the way we see here from the coarser scale to finer scales, then that is a clear indication of the presence of a singularity. Of course, this is a qualitative statement. Now, we need to quantify this statement further, and for that purpose we first quantify what we mean by regularity or singularity. See, regularity and singularity are complementary characteristics of each other. If a signal is regular or a function is regular, then there are no discontinuities, it is essentially smooth. Singularity is the complete breakdown of regularity at a particular point. And the problem of quantifying regularity was studied long ago in the mathematics literature. We have two measures which are basically use the same definition. These measures are known as Lipschitz regularity or Holder exponent. As I said, both use the same definition. What is the basic idea? Well, the basic idea is to see how well a function can be approximated by a polynomial of a certain degree locally. So, when we talk about regularity of a function or a signal, we can talk about the local behavior of the function or the global behavior of the function. The first thing to do would be to define the local regularity and then extend it to an interval. Before I really give you the mathematical definition of Lipschitz regularity or the Holder exponent, intuitively what these measures do is they provide a bound on the error that you incur by approximating f of t locally with a polynomial of certain degree. So, in other words, you are breaking up the function into two parts, a polynomial at nu. So, nu is the point of interest to us. We would like to know if there is a singularity there. At that point, we approximate the function with a polynomial, and epsilon is the error incurred due to that approximation. Of course, if f of t is exactly the polynomial, then the error is 0. What these measures give is essentially a bound on this error expressed in a certain fashion, and both, as I said, local and global measures can be provided. Now, it turns out that the vanishing moments property of a wavelet is the key to measuring this Lipschitz regularity or the Holder exponent. So, the basic idea is to perform a wavelet analysis and get an estimate of this Holder's exponent, which we denote by alpha, and I will define in the next slide. So, the vanishing moments of the property, if you recall, is the ability of the wavelet to locally approximate the function with a polynomial of a certain degree. So, whatever is left out will be reflected in the CWT. So, that is the basic idea. If I have a wavelet with p vanishing moments, recall, it can approximate a polynomial exactly it can exactly approximate a polynomial of degree p minus 1. So, what if your function has more than this polynomial, then that will appear in your epsilon, and you can use that to quantify the regularity or the Holder exponent. So, that is the basic idea. And of course, Fourier transforms will also be able to give you, but unfortunately they give you a measure of global regularity, that is how the function behaves overall in time, not how not the local regularity, which is what we are interested in. So, before we learn, of course, how to use the CWT for quantifying this regularity, we need now the definition of the Lipschitz regularity or the Holder exponent itself. As I mentioned, the basic idea is to approximate f of t with a polynomial, and then the measure is going to give you a bound on the error. So, PV of t is the polynomial approximation of f of t at a point nu, where I am interested in assessing the regularity of f of t. And what is this polynomial? This polynomial is nothing but the Taylor series expansion of f of t around nu up to the desired order. What order? M. The order here is denoted by m. So, what we are doing is essentially replacing f of t with a Taylor series approximation up to order m, and then consolidating all the remaining terms into an error term. And what Lipschitz regularity is doing is it is basically giving a bound on that error, and the exponent of this bound is the Lipschitz regularity. So, it says if the error is, if you can show that the error in your approximation can be the bound on the error in the approximation can be expressed as k times modulus t minus v raised to alpha, and that there exists a k greater than 0, then alpha becomes the Lipschitz regularity or the Holder's exponent. So, you can see this as a generalization of the error that you get from Taylor series approximation. And any function is said to be uniformly regular over some interval if it satisfies this expression. That is, at every point in the interval you should be able to show that there exists a k and an alpha such that the error is bounded in this fashion, and this k should be the same at all points in this interval. Then we say that f of t is uniformly regular or uniformly Lipschitz and so on over that interval, and this k should be independent of that of where you are looking at that in the interval. Now, what we would like to know is how to detect singularities. What has the Lipschitz regularity got to do with singularity? Well, a value of alpha equals 0 at any point nu implies that f of t has a singularity there. So, that is the key. So, if I find from my CWT that alpha is 0, then I conclude that there is a singularity. We can still do it visually, but here we are able to do it quantitatively, and that is the most important thing. And any value of alpha between 0 and 1 means that f of t is not differentiable at that point, and the value of alpha characterizes the type of singularity. We do not go too much into this aspect at this moment, but let us look at things with an example. And before we do that, the main result is as follows. What we have learned just now is how to quantify singularities or regularity. Now, we are turning to what feature of CWT will help me estimate that Lipschitz regularity or Holder's exponent alpha. That is the thing. So, two things, the definition of regularity or quantification of regularity, which is given by the Holder's exponent alpha, and now we are searching for features in CWT which will allow me to estimate that alpha. That is the point. Now, it turns out that you can prove, we will avoid all the theoretical proofs, that singularities are detected by determining the time at which the modulus maxima of the CWT converge at fine scales. Now, we have looked at this in the case of the impulse, we have looked at how the modulus converges, we have not looked at modulus maxima. What is this modulus maxima? Well, the modulus maxima is the line, is the maximum of the modulus locally at a certain scale or at a certain time. In fact, here we are interested in certain time. So, I pick a time t and I see locally what is the maximum, then that we call as a modulus maxima. So, I can now construct modulus maxima in the entire time scale plane, and all I have to do is follow the line that goes from the coarse scales to the fine scales. If there is a line that goes from coarse to fine, and at whatever point this line converges, at that point there is a discontinuity. When I show you the example, it will be a lot more clearer to you. So, that is the first feature, that we follow the lines of modulus maxima, and the second one is that it is necessary to use a Gaussian derivative wavelet for best results. That is, if you do not want any ambiguities, what kind of ambiguities can arise? Well, what can happen is, even if there is no singularity, you may still end up getting a line that is a modulus maxima line that will converge from coarse to fine scales, as I will show you in the example which I have borrowed from Mallet's book. And if you to resolve that ambiguity, it is best to use a Mexican hat or a Gaussian derivative type wavelets. You could use other wavelets, but then you may run into some ambiguities. And consequently, now as a virtue of what we have stated, if the wavelet transform has no modulus maxima at these scales, then x of t is locally regular. We are assuming that we are going to use a real wavelet here, we are not using a complex wavelet. Therefore, whether you talk of Tx or not the modulus, then magnitude, it should be fine. Essentially, if t has no modulus maxima at fine scales, then x of t is locally regular. You could have modulus maxima at coarse scales also. And secondly, we would like to get an estimate of alpha. Suppose there is no singularity, exact discontinuity, but a breakdown of the differentiability of f, which is also important in signal analysis and more so in image analysis, where you are looking at edge detection in images. You would like to know what kind of edges you have, discontinuities you have run into, whether it is a singularity or a breakdown of the differentiability of f. In other words, we would like to estimate alpha, because alpha characterizes the type of singularity. Again, we keep away all the theoretical results, you can show that the modulus of the wavelet transform or the magnitude of the wavelet transform is bounded above by this factor a times, where a is a constant, a times s to the alpha plus half, where alpha is the same Holder's exponent or the Lipschitz regularity that we just learnt. So, what I do is I plot a logarithm of the magnitude of CWT versus log 2s and look at the slope, and from the slope I infer alpha. So, that is the basic idea. So, let us look at an example which I have borrowed from Mallet's book. In fact, this example has been reproduced with the help of Wavelab, which has a very nice feature. You can there is a directory in WaveLab which contains all the codes for reproducing the entire set of figures in Mallet's book, and I have borrowed the code corresponding to this chapter. This figure appears in chapter 6 of Mallet's book. I am not talking of the latest edition, but the previous edition. And here Mallet uses a very nice signal. It is called a piecewise regular polynomial, you can say so. So here you have discontinuities of different types. So here in the beginning I have a discontinuity here, and then a smoother one, because this kind of a jump is different from the jump that you see here. More importantly, the cusp kind of jump that you see at t equals 108 is different from the kind of discontinuity that you see at t equals 14. So let us look at the magnitude of the CWT plot, which has been computed using a Gaussian derivative, that is a Mexican hat wavelet. If you see here, the magnitude of the CWT converges from coarse to finer scales at several points, especially where there are discontinuities. So look at t equals 14, that is at time 14, and then the next one here. And then you have, of course, a convergence of coarse to fine scales, but if you look at the color bar, the intensity of this is very weak. Now this is the problem that you can run into if you only follow the feature which goes from coarse to fine scales. That is, we said singularities are detected by following the lines that converge from coarse to fine scales. If you only use that feature, then you may run into some ambiguities. It is better to always look at the Holder's exponent also to get a feel of what kind of discontinuity, whether it is a singularity or some other kind of discontinuity and so on. So you can see wherever there is a jump in the signal, you see this feature of CWT converging from coarse to fine scales. Now rather than just visually looking at it, it is nice to draw the modulus maxima lines that you see at the bottom, again generated by the code given in WaveLab. And you can see the difference in the way these lines converge. So for example, if I look at the discontinuity at time t equals 14, there is a line that starts from coarse scales, that is high scales, and then converges to fine scales. Whereas if I look at the next discontinuity, the line really does not follow, that is, it does not start off from the coarse scales. You only see some kind of a maximum line, the modulus maxima line, that starts off from relatively finer scales to even more finer scales. This does not mean there is no discontinuity, but this discontinuity here at the second point here is not as sharp as the one that you see here. In fact, when we look at the cusp that you have here at this point at t equals 108, that discontinuity is also different. So as we just said, we would like to really quantify rather than keep qualitatively classifying these discontinuities. As is done in Mallet's book, I have picked two modulus maxima lines here corresponding to times t equals 14 and t equals 108, and plotted the logarithm of the CWT versus the logarithm of the scale. Why did I do that? This is based on the result given 4. Remember, when we plot this, the slope of this will get me an estimate of alpha. So if I look at the blue line here corresponding to t equals 14, the slope of it is roughly half if you look at the slope, and therefore that gets me alpha equals 0, whereas for the red dashed line, which corresponds to the modulus maxima line at t equals 108, the slope is approximately 1, which means alpha is half. Both are indicating the discontinuities, but they are of different types. This is a perfect singularity here for the function at t equals 14, whereas at the cusp it is more of a loss of differentiability for f. Of course, there is some kind of discontinuity here, but you see visually itself you can see there is a difference between the type of discontinuities here, and this is how you quantify singularities or regularities using CWT. There are a number of other examples that are given not in Mallet's book, but in a book that, let me just take you to the reference in this book here by Misiti and others. you should look up the concluding chapters where they talk of number of applications of wavelets, and one of those applications is the singularity detection, where they show you how you could really use the Holder's compute the Holder's exponent from CWT and classify the type of singularity. Let me take you back now.